Our first speaker for today is Professor Robert Dalrymple. Professor Robert Dalrymple is currently Professor Emeritus of Civil Engineering in Johns Hopkins University, as well as Distinguished Professor of Coastal Engineering in Northwestern University. His research has been in the field of coastal engineering, including waterways and their impacts on shorelines, structures, the ocean bottom, and natural hazards such as rip currents, and tsunami. Without further ado, let us invite Prof. Dalrymple to present on future sea levels, causes, and consequences. Prof. Dalrymple, please.
Thank you. Pleased to be here in my first visit to Singapore, and I've been very pleased with what I've seen since I've been here. I'm basically giving a talk to set up the rest of the other talks, to talk about sea level rise. And I will mostly talk about the causes and maybe a little bit about consequences, but the other speakers will be talking about consequences. But just to give you a preview, is the consequences are already here. That high tides in many places of the world, high tides, that is the more extreme high tides during the month, are already causing flooding. So you see, this is Miami. It's flooded on the streets and there's no rain. If it was raining, it would be worse, but there's no rain. So this is nuisance tides or king tides or excessive high tides, perigean spring tides, lots of names for this phenomena, but these are just the highest tides during the month or during the year. This is what's going to make people really concerned about sea level rise. It's not inundation by sea level. It's the fact that the high tides will cause people in Miami to move out. So if we're talking about coastal flooding, as PUB is concerned with, excuse me very much. So I'm going to talk about sea level. Oops, I just turned myself off. Well, I'm pretty close. So I'm going to talk about sea level and sea level rise. I just mentioned tides, but we have to worry about other things that cause the water levels to change at the coast. So storm surge, waves set up the additional rise of water due to waves. And then you've got rain and subsidence of the ground. And there are a number of things that contribute to sea level. But let's go back in history and look at what's happened since the last glacial maximum. So over 20,000 years ago, sea levels were down by 135 meters. Think about how big Singapore was at that time. But then as time went by, the glacier started to recede. Sea level started climbing until about 8,000 years ago. During this time, sea level was advancing about 1.6 centimeters per year. That's an important number to remember. And then about 8,000 years ago, the rate of rise slowed, and it's been roughly constant for 8,000 years. One important factor is that when we look at this change in the curve, at that time, the sea level slowed down enough that river deltas could survive the inundation by the rising tide. So if you look at deltas around the world and you date how long has that delta been there, it's 8,000 years. So if the sea level is faster than that, then deltas die. So let's talk about the causes of sea level rise. In red, I've highlighted ice melt. So this is glaciers retreating, ice sheets melting. So we'll talk about that quite a bit. Then there are density changes. So, you know, the oceans of the world are huge. There's immense volume of water. As we start to heat that water with global warming, it expands. So that's called a steric effect. And it expands, and it doesn't have to expand much, but when you have kilometers of water depth, all that adds up and the sea level expands or rises. But then there are a lot of other effects locally with sea level, and that is glacial isostatic adjustment. That's due to the fact as the land is unburdened by the ice, then the land comes up. And so that's a local effect, uplift and subsidence. In the US, we pump oil out of the ground, we pump water out of the ground, and the land sinks. So that's a local effect. Another effect that's bigger than you would think is terrestrial water storage. So building dams actually affects sea level, surprisingly enough. So we'll talk about these things. But why is the ice melting? Because it's getting warmer, as you know. So this is since 1850, looking at global temperatures. It almost looks exponential right now. Just last month, the World Meteorological Organization said in the next 5 years, one of the years will be 1.5 degrees C above the industrial era. And that's what, we're trying not to go above 1.5 degrees C, but we're going to hit it in the next 5 years, probably. The other thing to note about this chart is, so this is 100 years from here to here. So if we're going out to 2100, let's see, that's about over here someplace. So if we try to extrapolate that curve, if things stay on the same course, we're going to be way above 1.5, but 2 and 3 and 4. I mean, you extrapolate to 2100, about something like that. So the problem is serious. If we look at the reasons we have warming, I mean, the Earth is supposed to be in equilibrium. The sun provides energy, ground heats up, radiates it back to the space. And as long as that's in balance, then the Earth has a constant temperature. But if we prevent the back radiation, then the Earth heats up. And so what's happening is we're putting CO2 into the atmosphere. CO2 stops some of that back radiation, the space of energy, and then we get warming. But this is 800,000 years, as best as people can determine, of what CO2 is. This is in parts per million, so the numbers are small. 0.04% of the atmosphere is CO2. It's a very small percentage, but it's very powerful. This is where we are now. So it's not a natural, the number today is not a natural number over the last 800,000 years. It has been worse in the past. So we've had much more CO2 in the atmosphere, much more than we do now. But those were associated with extinction events. So we don't want to go there. If we look really closely, what is it now? So I looked at it in May 16th, 421 parts per million. This is when I went to college. And so since I went to college, it's gone up 32%. So we're living in this big chemistry experiment where we're dumping CO2 into the atmosphere. We're in the experiment. And we're not the control group, we're the experiment. And, so we have the unintended consequences of what all this is going to do. There are other greenhouse gases more powerful than CO2, such as methane and nitrous oxide. There's very, very tiny percentages of the atmosphere, but they're far more powerful than CO2 at blocking radiation. And look at how their concentrations have been climbing. All right, so who's keeping track of all this? Sorry, who's keeping track of all this besides the individual researchers around the world is the IPCC, Intergovernmental Panel on Climate Change. And what they periodically do, as you probably know, is that they get hundreds of scientists to write sections about the risk of climate change, its impacts, and what things we might do to mitigate it. This is an immense undertaking. They periodically produce reports So assessment report number 6 recently came out. It's 8,000 pages of summarizing the current research on these topics. So this is sort of the go-to place besides the literature. Besides the literature, this summarizes what the literature is. So what do the scientists use for tools? Well, to see how the ocean is warming up. There's the Argo project with about 4,000 drifters that are going around the world, drifting and then sinking down 2,000 meters, measuring temperature and salinity. There are tide gauges that we can use. There's the Amazing Grace project, which are 2 satellites that are going around the world. When the first, and they're closely tied together and they're measuring the distance between each other. When the first one goes over ice, where there's more mass locally than other places, it speeds up because of the gravitational attraction. The second satellite realizes that they're going apart. Then the second satellite goes over the ice and it gets attracted. And from the differences in distance, they can determine the mass below. And then there's satellites for hurricanes and typhoons. There are lots of instruments to look at the effects of storms and what's happening in storms. I like this because this is called a sail drone, measuring temperature and salinity, wave heights, and so forth. You can steer it right into a hurricane. So what's the big problem? So here's an ice sheet. Ice sheets hold tremendous amounts of ice, and they accumulate mass by snow. And then the pressure of the snow causes the ice to move, tries to flatten out and moves to the sea. Then it either melts or calves. And that can be in equilibrium, and has been in equilibrium for quite a while until recently. These ice sheets are immense. So ice in Antarctica is almost 5 kilometers thick. There's hundreds of thousands of gigatons of ice there. Greenland is also very big. So these are our biggest sources of ice in the world. They're equivalent, if they all melted, Antarctica alone would raise sea level 58 meters. Greenland, if you melted it, would raise it 7 meters. And then we have the glaciers that are retreating rapidly, but their contribution is not that big. You melt them all, but it's the ice sheets. And so using the Grace satellite, here's the melting going on in Greenland and Antarctica. This is the Amundsen Sea. You've probably heard of the Thwaites Glacier and Pine Island Glacier. These are causes of concern. But the melting is 277 gigatons of ice. That's 10 to the 12th kilograms of ice, and 151 gigatons of ice per year. Add that together, it only counts for a little over a centimeter or a millimeter of ice, sea level equivalent, right? So melting the total of this one and this one only accounts for 1.2 millimeters of sea level rise. The ocean surface is big. You need a lot of ice to melt to raise it. All right, so if we look at historical sea level rise, I've talked about that a little bit. Then we zoom in on this little current section. Here's the last 2,500 years. You can see that sea level is rapidly rising now. We zoom in again. We see this curve. From here to here, this period of time, the rate of rise is 1.32 millimeters per year. If we even zoom in further, we're up to about 3.6 millimeters per year. So the sea level is rising, but it's also accelerating. The acceleration term is over the next 70-something years is going to be large. The contributions of the warming of the seas, the melting of the ice. If you add those together, you get basically what's observed. So those are the key components. One little point to mention is this breaks down the amount of water added to the oceans. This thing is the terrestrial effect. So the sea level was kind of constant for a while, and we were damming up a lot of rivers, and that had a big effect, far more than I expected. Purpose of this slide is to show you that between two different time periods using satellite altimetry, that the sea level is rising around the US. So we have models to predict the future. I don't have time to get into the models, but these are very sophisticated models, many groups building models and predicting the future. And they're using 5 different socioeconomic pathways. So these are how we assume the future is going to develop. And so what they do is they keep running these models with different starting conditions, choosing one of these scenarios and see what happens. And so what you see is when you look at all the models and all the different starting conditions, you get a spread of results depending on what your initial assumption is. You know, which of the pathways did they assume? If you take the worst case, that is to say we continue living the way we've been living in the past, then you can see that their temperature change is quite large. So what Singapore doesn't need is another 3 degrees C of temperature rise. Precipitation is also projected to change into the future. When we get to sea level, so here are the worst case projections. This is 1 meter. And this is since 1900. So relative to 1900, we're getting up towards a meter, so maybe 90 centimeters. This is the best case if we reform our ways, and it's still significantly above 1900. This is the worst case, where we assume that the glaciers, the Pine Island glaciers and the Thwaites glaciers, become unstable and start sliding off Antarctica and cause the sea level to rise dramatically. So we definitely don't want this to happen. Oops, I think I went too many. The point of this slide is the previous one was at 2100. If you put all the CO2 into the atmosphere that's causing the heating, sea level is not going to stop at 2100. It's going to continue. And so you can see the curves just keep going on and on after 2150. If you go out to 2300, so this is a long period of time, then in the worst case scenario, this band is, I think it's 17, you have your median and you've got 17% in the 83 percentile range. And so there's this huge range, but we're talking 3, 4, 5 meters of water at 2300. So the process is started. CO2 stays in the atmosphere for 200 years. So when we put the CO2 in, it's there for essentially forever, for our point of view. The only purpose of this slide is to look at the rates. So this is what happens if we get to 1.5 degrees C at 2100 or 3 degrees C. So we have a range of sea levels, but we also have rates of rise. Now remember I said it was 1.6 centimeters per year when the glaciers were melting 20,000 years ago to 8,000 years ago. Well, we can almost get up to that rate. We're approaching that rate. And if you look at the extremes, these are dangerous conditions. Why that's important is wetlands, where our fishes are breeding and hatching and so forth. The wetlands have a hard time keeping up with sea level rise. They need sediment. They need to be very productive to rise with the sea. And there are estimates that say you can't grow a wetland if the rate of rise is too high. Now, to finish up, my experience with sea level rise is this disaster case, which is the delta of the Mississippi River. Sea level is playing a role here. There are multiple other factors playing a role, but what is red is lost. So all this land is lost, and during that period of time, the Mississippi River discharging sediment has created land only here and only here at the end of the delta. So this is the worst case scenario. Finally, here are consequences. I won't go into them because you'll hear more about consequences. But this is Venice during high water. And, you know, this is a World Heritage Site. And so we're in danger of losing, you know, a lot of our heritage with sea level rise. But there are all these consequences that we have to worry about. And I'll leave that to my colleagues to discuss. Thank you.